So in this lesson we're going to be going through a sample organic chemistry unit 3 test. So hopefully this will help you in revising for your actual SAC or test at school. So the first question is state the name of the homologous series to which each of the following compounds belongs. So you're basically just naming what group you can see, what functional group you can see. So in this question, in this molecule here, you can see an OH. We know that OH belongs to it's a hydroxide. It belongs to the alkanol. Functional group, and that's the homologous series to which it belongs to. Yes, you would be wrong if you said alcohol, because alcohol is considered, it's the equivalent of ethanol in our culture, and so technically you should say alkanol. Okay? In this situation here, we have a functional group right there. And from your knowledge of a COO bond in the middle or somewhere in between the molecule, it belongs to an ester functional group. Okay. In this situation, we have a chloroalkane because we've got a chlorine functional group, and this is an alkane, so chloroalkane. In this situation here, our functional group is COOH, so that is a carboxylic acid. And finally, in this last one, we have an NH2 group there, and it is known as an amine functional group. So this is just testing the knowledge of whether you know whether you can see what the functional group is and what family it belongs to. So that's an important thing to know before you go into your test. Okay, so you want to have a very good understanding of what kind of functional group is present and what is it called, and also what homologous series it belongs to. Question 2 says draw structural formulas to represent the following compounds. So with structural formulas, you have to draw out the whole molecule, showing each and every single bond in it. Okay, so with to start with the drawing, you begin from the back. So I would get the longest chain first. We know that butane contains 4 carbons. So generally we draw them zigzag to show that there's minimal bonding strain between each of the atoms. And on the second carbon, which is this one, or could be possibly this one, depending on whether you count left to right or right to left, I'll just put it here. The methyl functional group is just a CH3 bond, but you do need to show each and every one of those hydrogens, which I cannot fit here, but I hope you get the idea. And each of the hydrogens here must be also shown. So that carbon has one last hydrogen. Yeah, it's easy to get lazy in these kind of drawings, so please don't. Not in your test or your SAC at least. Okay, so that's how you draw the molecule out. The next one, let's have a look. So it asks you to draw 1,1,1 trichloroethane. So let's start with the ethane. Alright, so we've got ethane has 2 carbons. Okay, now there's something going on here, something strange. 1, 1, 1, and then trichloro. So on the very first carbon here, or here, depending again where you start counting from, on this very first carbon here, you've got 3 bonds to chlorine. That's why it's trichloro, and that's why it's all 1. Because this is on the first carbon, this one's on the first carbon, so is that. And that's just the convention that chemists use. So you do have to indicate first of all the position of them and then how many of them you have. Okay? So let's have a look at the next one. So we've got 1-chlorohex-3-ene. Okay, so the hex-3-ene, we'll just draw a hexane first. How many is that? That's 5, 6. And on the third carbon we have, so 1, 2, 3. On this third carbon here we have a double bond. Okay? And then on the first carbon we have a chloro group. So that's what it looks like. And on this carbon here we just have 1 hydrogen like so. And there we go. That's our molecule. Okay, so then we have pentanoic acid. So pentanoic acid, this is a carboxylic functional group. So we have to draw 5 carbons. And on the 5th carbon we have a double bond OH. And yeah, it's usually important to split the O and the H together when you're drawing a structural formula. Depends on how picky your teacher is, of course, but I'll just stay on the safe side. But yes, here we go. That's pentanoic acid. I believe that's 5 carbons. Yep. So that's the carboxylic functional group at the end there. Alright, so let's have a look at question 3. Okay, whoop, I went a bit too far. Computer's being a bit temperamental today, so we'll try to not annoy it too much. Alright, so state the name of the following organic compounds given the condensed semi-structural formulas. So here we have our semi-structural formulas. If you feel better about it, you can draw it out. So we can see here this ending is an aldehyde. So that's an aldehyde. And our rule for naming aldehyde, we first count how many carbons we have. So we have 3 of them here. So it's propane. But obviously this is not propane, right? We have a aldehyde group at the end, so instead of it we call it propanal. We get the E, throw it out, and replace it with al. Propanal. Okay. In this case, we have a functional group here in the middle. That doesn't look like an ester. Okay. If I make some more space for this question, that might be good if the computer... Oh, there we go. It's cooperating. Okay, so we can draw it out. CH. Okay, so we have double bond O connected to a CH H. Okay, so we have this molecule here. Now, before, you can see the difference between an aldehyde and this type of molecule is that aldehyde has the double bonds OH at the end. Okay, in this situation we have it in the middle of our molecules, in between two carbons. So this is actually known as a ketone. Okay, and ketones have the ending, well, normally it would just be 1, 2, 3, 4. So we know 4 is butane. Ketones usually have replaced the E with an O-N-E. So butanon. And because the carbon is, this ketone is on the second carbon, you can call it 2-butanon. Okay, so, or you can of course place it in there if you wanted to. Butan 2-on. Okay, it depends on your preference. Sometimes this is more appropriate, especially if you happen to have, like, say, if that was a chlorine group there and you needed to also provide a number for that chlorine group, then this format here would be more appropriate, because then you could say, okay, well then that's on the 4th carbon, because you would have to assign the most important functional group. You would have to count from here in this case, because the ketone is more important than the chlorine, so the ketone needs the lower number. Okay, so that would be in that case called 4-chloro-butan-2-one. Okay, so that's how you name something a little bit more complex, but we'll move on. So, okay, so we've got this one here. It looks like a chlorine. It's got 2 chlorines, so it might be worth drawing out. So H, and then this chlorine is here, and then it's connected to another C, H, and another chlorine here. Okay, so it looks like it's just a normal single bonded carbon molecule, so it's an alkane. And in this case it would be considered a ethane. Okay, but you can see we've got a chlorine functional group here and one here, so I'll probably need more space, so I might shift this over. So because on the first carbon you have carbon number 1 and carbon number 2, you have a chlorine group. You would have to give the positions first, relative positions, so 1, 2, and then you would have to say that there are 2, so you use di-chloroethane. Okay, so that would be the name of the molecule. Alright, let's have a look at the next one. Sorry, as I'm attempting to scroll down. Alright, now this one here, again, helpful to draw out because you never know what's going on in terms of the bonds there, unless you can very clearly see it. So there's a H there, and then it's connected to another carbon with one H there. Now you can see that there's bonds missing here. That carbon only has 3 bonds, so there needs to be a double bond here. And then that's CHH. Then again it's the CHH. And finally CH3. Okay, so we have our double bond right here. So in terms of naming this, we will count from the side that gives that double bond the lowest number. So in this case we'll start from left to right. So on the second carbon we have this double bond. Okay, so we know that there's 1, 2, 3, 4, 5, 6 carbons. So this would be considered, you can name it in 2 ways. You could say 2-hexene, or you can say hex 2-ene. And I recommend using the second format because if there's any other functional group, and there could be, on this molecule again, that 2 at the front will get confusing. Okay, so stick to the second format, just to avoid confusion for yourself. Okay, let's have a look at naming the next one. Alright, so we've got a HCOOH, so that is a carboxylic functional group. Alright, and we've got double bond O, OH, and just a hydrogen here. Okay, so in terms of naming this, it's just got 1 carbon. Okay, so and it's a carboxylic acid, so it's methanoic acid. Alright, that's how we would name that one. Alright, let's go to the next one. That wasn't the next one, but okay. Alright, so here we have, again, I prefer drawing these. So CH3, CH2, CH, and then this OH must be coming off here because we don't have enough bonds there. And it's important to bond this carbon to the oxygen, not the carbon to the hydrogen, okay? Because the hydrogen's coming off the oxygen, so that's important when you're drawing it. Okay, so you can see we have our alkanol or our hydroxyl functional group there. Now, in terms of naming this, again, we start from the side that gives the lowest number to this hydroxyl functional group here. So 1, 2, 3, 1, 2, 3. It really doesn't matter what side you count from, as long as you just get the right name. So this is 5 carbons long, so it would be considered pentanol. But because this OH functional group is on the 3rd carbon, we would call it pentan 3-ol. Okay. Or you could also put the 3 in front of here, which is not recommended, but you can do it. Wouldn't be wrong in this situation. Okay, let's go on to question 4. So, just gonna scroll this. Okay, so state the name of the molecule shown below. So this is the same kind of work that we did before, except now we're looking at it from the perspective of a structural formula. So it looks like we have to identify our longest chain first. So we have our longest chain right there, 4 carbons long, and this is our methyl functional group. Okay, so for the first one, that methyl functional group, it exists on the 2nd carbon. We won't count from this side because that would mean that the methyl is on the 3rd carbon, which is, we always stick to the lowest number. So 2-methyl butane. 2-methyl butane. Okay. On this figure here, we have our functional group here and a functional group there. Again, we need to just identify our longest chain, which is 4 carbons long, as you can see there. Now, it doesn't matter, I think it doesn't matter where you start counting from. 1, 2, 1, 2. Because in both cases, you're going to have the lowest number for each of the chlorines. So we have a chlorine, let's start counting from there. You'll see it doesn't matter if you start counting from the other side, but you can test that out if you wish. On the 2nd carbon and on the 3rd carbon, there is a chlorine group. So we have 2, 3 dichloro, and this would be butane. Okay. Alright, so in this diagram, this is our functional group, it's our ketone, and you can see that that's on the 2nd carbon from this side. And we have 4 carbons, so this is going to be called butane on. But because it's on the 2nd carbon, it's butane suon. That's the name of the molecule. Okay, so let's have a look at this one. So we have an aldehyde here. It's not an it's not a carboxylic, it's an aldehyde. And this is 1, 2, 3, 4, 5. So it's prop would be 3. This is pentanal. Okay, and you don't have to give the position for that because it's obvious that it will be at the end, because the aldehydes are always contain the COH bond, whereas ketones just contain the CO. Alright, now in this situation we have the functional group right there, and we know that that's a carboxylic acid. Counting how many carbons there are, 1, 2, 3. So this would be propanoic acid. Okay. So moving on. Question 5. The formula of a group of related molecules are all these. Okay. State the name that is given to such group of compounds. Well, anything with an NH2 group is called an amine. Okay. And so question B asks, how would you expect the boiling points of these compounds to change with increasing numbers of carbon atoms? Explain. So probably need a little bit more space for that one. Okay. So now what happens when you have when you're considering the boiling point of compounds? The rule is that the larger or heavier the molecule, the greater the boiling point or melting point, due to greater dispersion forces. So dispersion forces are just forces essentially between atoms. Okay, so the greater amount of atoms you have in a molecule, the greater the dispersion forces, and therefore that changes the property of the molecule. So in this case, related to this example, you can see that, I mean, this compound here is the lightest one out of all of them, and I believe this one here is the heaviest one. So this one here would have the lowest boiling point because it has the least dispersion forces. You can give that as an example depending on how much marks this is worth, but it doesn't state that. Whereas this is an increased boiling point because it's just larger, it has more atoms, and the dispersion forces are going to be more significant. Okay, so compared to alkanes of similar molar masses, state whether you would expect these compounds to be more or less soluble in water, or more, what is that meant to be? More or less volatile. Okay, so now we're making comparisons. Alright. Now, amines have an NH2 group. Amines have an NH2 group, so I'll write that down. Amines have an NH2 group, functional group. And this makes highly polar. Okay. Basically, alkanes are just usually chains of carbons and hydrogens and that's not polar at all. Okay, that's not soluble in water at all. So alkanes don't have polar functional groups. Therefore less soluble in water. So what would happen, the solubility is quite interesting because the most soluble compound here out of this list, even though they're all amines, they're all going to be soluble, is actually this one. This one will be most soluble in water. And then this one will be least soluble. And the reason for the difference is because that NH2 group, which is quite polar, is being shared across only 2 carbons. This NH2 group here is being shared across 6 carbons. So meaning that the 6 carbons, the non-NH2 group is becoming, so the non-polar section, which is this part here, is becoming larger. Okay, so that means that the solubility of this molecule decreases and the solubility of this molecule increases. Okay, so let's have a look at next question, which is more or less volatile. Now, volatile means that the ability of something to turn into gas. And so volatile is ability of something, usually a molecule, to turn into gas. Now this has everything to do with, depends on the intermolecular bonding. If you think about water, water has a lot of intermolecular bonding, and we know that that's what keeps it liquid at room temperature. The fact that water interacts with other water molecules and they hold on to one another, the molecules actually connect together and interact together, means that they're more resistant to turning into gas. So if we compare our amine groups, will have, well, they have polar ends, don't they? They're polar. Amines are polar because they have the NH2 group. So as a result, they will connect together more strongly than in comparison to the alkanes. So in this situation, we can say that alkanes will have greater volatility. Okay, since due to lower intermolecular forces. Okay, so I'll split this up into a two-part video. So this is it for this part, and then there will be a continuation video where we'll go through the rest of the questions. So thank you for listening so far. Hope that you gained something from that.